which is, I'm now in my notes on section 1.6, and that would be question B, 1B for 1.6, says draw the following, and that's, I've been given this. This is like the given picture. It isn't one of our BFFs, it's just some random shape, and you're going to move it 1 unit to the left. So that means every one of these points is going 1 unit to the left. That is the only change, right? So if this is the point, I'll just start with the first one. Yeah. So if that's the point -2, -3, then that point is going to move over 1, and it's going to be at -3, -3. And if this one is at -1, 0, it will now be at -2, 0. And this one, which is at 0, 1, will now be at -1, 1. Everything is going over to the left 1 unit. So where's this going to end up? If it goes left 1 unit, it's going to be at the origin. And this one, which is at 2 now, is going to be backed up to 1. And that one, which is at 3, is going to be at 2. Everything's just going left 1. It's no mystery. This is 1, 2, 3, 4, 2. So it's going to be at 3, 2. And then I'll just connect my dots. And I should have exactly the same shape, just moved over 1 unit to the left. Now, because I'm not using graph paper, some of mine may look not quite exactly the same shape, but if you're doing it on graph paper, it will look exactly the same. All right, is that okay with everybody? If you are adding or subtracting inside the parentheses, just like always, that's a left and right movement. Okay, now, what about this one? We talked about that one too. What happens to the picture when you put a negative out in front of it? Flips upside down. Now, the technical term for that is that's a reflection across the x-axis, which is simply the fancy math way of saying upside down. So what does that mean? Well, this point right here, which was originally -2, -3, is now going to be at -2, +3. Does that make sense to everyone? You're flipping it upside down. You're flipping it across the x-axis. If you're going across the x-axis, if you start down here, you're going to end up here, right? It's a vertical movement. All right, what about this guy? What's going to happen to him? He is sitting on the x-axis. He's not moving. So that one's just staying right where he is. This one, which is up 1, will now be down 1. That one will stay the same. Now, this one is down 2, so he's going to be flipped up 2. That one just stays put. And then let's see, this one's up 2, so he's going to be down 2. So when you connect those with a nice smooth curve, you should have exactly what you started with, just upside down. Is that okay? Seems easy enough. Now this one we haven't talked about. Does anyone have an idea about what it does to your picture when you put a coefficient out in front of it? Like this happens to be a 2, but it could be any other number. Jacob?
Was it expand a line?
It makes it, this one is going to be twice as tall. So this number right here multiplies the height of the curve. So however tall it was, it multiplies y, in other words. So however tall the original was, whatever the y was in the original, it's now going to be doubled. So go back to the original picture. All right, now wait a minute. This guy is down -3. If I make that twice as tall, he is now going to be down to -6. The y's get multiplied. It's twice as tall as it was. So it used to go down. These are all running together. It used to go down to -3. Well, now it's going to go all the way down to -6. So that's the point to -6. Because my y got doubled. That should make sense to you because do you remember that f of x is just another way of saying y? So this is like 2y. This is doubling the y's. All right, so there's the first one. All right, now what about this guy? He stays the same. What's the y coordinate right here? 0. 0 times 2 is 0. So that point hasn't changed. What about this one though? That y is 1. So now he's going to be up at 2. This one's going to stay the same because it's 0. All right, now look at this one. He's going down 2. So the new point will be down 4. We got double. This one's going to stay the same. And that one is up 2, so he will now be up 4. So connect those with a nice smooth curve. And for the first time, your shape is different. I mean, the general shape is the same, but it's definitely been stretched vertically. It's the same width, that part hasn't changed, but it's twice as tall as it was. This negative and this +1 did not change the size of the picture. This changed the size of the picture. It made it twice as tall. All right, everybody still with us? All right, let's see what else we've got. There's a couple more here for this. All right, now we've got some absolute value transformation. So we're still using this original picture. But now we've got some absolute values. Now there's two ways, and you can see them here in the problems. There's two ways that absolute values can be introduced into the problem. One is the absolute value of the whole thing. All right. What impact does taking the absolute value of the whole thing have? Well, this is pretty easy because you know that when you take the absolute value of something, it becomes positive, right? That's what absolute value does. It makes everything positive. So when I look at this curve, this part and this part are already positive. These are positive y values. So that part of the picture is going to stay exactly the same. The positive parts don't get changed. So that part right there is going to stay the same. Anything above the x-axis is positive, and it isn't going to change. When you take the absolute value of something positive, it just stays the same. But what happens to these negative parts? When you take the absolute value of a negative, it becomes positive. So this point, instead instead of being down 2, is going to be up 2. And this point, instead of being down 3, is going to be up 3. And there is the absolute value. So how do we sketch the absolute value of something? If it's already positive, it just stays. If it's negative, it gets flipped up. So all of the positive parts are right here. These are the positive parts. Anything above the x-axis. So those stayed exactly the same. I didn't do anything to those. But these have to get flipped up. We call this sometimes, it's sort of a weird math thing, but we call this sometimes the bottoms up function or transformation, because it takes everything on the bottom and flips it up. Okay? Now, that's different than this one. That is also an absolute value. But you see the absolute value is in a different place. So when you have the absolute value of just x, you draw everything on the right side. So all of the positive x's, you just draw. So I'm just going to redraw my picture exactly as it is on the right side. So I'm redrawing the right side of my picture, which is where x is positive. Okay? Any idea what happens on the other side? What's the absolute value of positive 2? What's the absolute value of negative 2? 2. Wait a minute. So when I take the absolute value of negative x's, I get exactly the same thing as when I did positive x's. So now do you have an idea what's happening on the other side, Josh? It's the same thing, it's a reflection. So you're going to have, this part of the picture is gone. It's gone. That is gone. Left side's history. And in its place, you have an exact reflection of this side. So this comes down like this comes down like this, and this comes up like this. So whatever was on the right side of the picture gets mirrored onto the left. So this causes the right to be mirrored on the left. What was originally on the left is gone. It has no place in this function. So, absolute value of the whole thing. Everything on the bottom gets folded up. Absolute value of just x. Everything on the right gets folded left. Okay. All right, now I have a new picture. We can start with whatever picture. There's nothing special about these things I'm starting with. They're just things I made up. So this picture There's my original picture. This is my function. Now I'm going to do f of negative x plus 2. So there are two things happening in this problem. F of negative x plus 2. Now, you know how it mattered where the absolute value was? Repositioning it makes a difference in the problem. Okay, where you put that negative makes a difference too. Look at the other negative we did. When we said it was going to be an upside down, where was it? Out in front, right? Out in front of the whole thing. When your negative is out in front of the whole thing, it reflects you across the x-axis. It turns you upside down. When your negative is on the x, guess what it does? It reflects you across the y-axis. So, I'm going to do this part first. I almost always do this is a two-step problem because there's two things going on. Some people do it the whole thing at once. I don't. You do whatever you want. I'm going to do it in 2 steps. So the first thing I'm going to do is take care of the negative. It's like the order of operations. I take care of the multiplications before I do the additions. So I'm going to take this picture right here, and I am going to flip it across the x-axis, or y-axis. I'm flipping it sideways. It goes across the y-axis. So, 1, 2, 3, that point ends up over here. That point ends up right there. This one ends up here. That one doesn't move. If I'm flipping you across the y-axis, that one doesn't move. This one goes here, here, and here. So this is my picture flipped across the y-axis. Does that make sense to everybody? Okay. Jacob?
So negative x, I'm sorry, any part of
The negative on the x flips you sideways. It's a sideways reflection across the y-axis. So what was on the left goes to the right, and what was on the right goes to the left.
and the plus 2.
Haven't done that yet. But we should know what that plus 2 does. Notice that plus 2 is not in the parentheses. It's on the end. What does that do? That's up 2. That's your up and down movement, and plus 2 means up 2. So you're going to take this picture right here, and you're going to move everything up 2. So it's easier with graph paper, I think, but you're okay. Oh, up 2. So this so far. It's up 2. And that's what I end up with. The purple one is what I end up with. If you're like me and you want to do it in 2 steps, just use a colored pencil for your final answer, or use a highlighter, highlight your final answer, whatever, just somehow indicate what your final answer is.
You don't have to show both, though.
You don't have to show both. If you can do it all at once, that's great. Hayden, did you send that to me?
Yes, I did.
All right, thank you. Okay, so now we've got another one. Now this is only a 1 step. There's only 1 transformation happening, but it's a different transformation because we talked about a minute ago, we had a number out in front, remember? And we said that number multiplied the height, right? So it was a 2, so our height got made twice as tall. If it had been a 3 or a 1/3, whatever that number is, this number out here multiplies the height. Any idea what that number might do? It impacts the width, but you need to be careful. All right, let's think about this for a minute. Remember when you have something like this? We know this does exactly what it looks like it's going to do. It goes up 2. But that's a plus 2. But it doesn't go plus 2. It actually goes back 2. Do you remember that? Anything inside here ends up doing the opposite of what you would think. If it's an x minus 3, it doesn't back up 3. It goes forward 3. So, the same thing is true of this. This number doesn't multiply the width, it actually divides the width. Well, wait a minute. If that number divides the width, we're dividing by a half, which is the same as multiplying by 2. So your first instinct was this was going to be half as wide. No, it's actually twice as wide. Anything on X is always opposite of what you think. So this picture is going to be twice as wide. The height hasn't been impacted, so all the points are going to be the same height. They're just going to be twice as far as they were. So, again, we're using the original. No, don't use this. We're using the original. This first point, if I just go in order, this first point is at -3. Now it's going to be at -6 because it's twice as far out. That point is twice as far out as it was. Now this one is at -2, so it's going to be at -4 and still just up 1. You're not impacting the height. So this is the point -2, 1. So now it's going to be the point -4, 1. This is -1, it's going to be at -2. So now I have, so far I have this. It's the same triangle, it's just been doubled in width because that was a 1/2. All right, what's going to happen to this point? Nothing. He's going to stay right where he's at. He's at 0, so he's not moving. This one, on the other hand, is going to be out here at 2. This one's at 2-1. He's going to 4-1. And that one's at 3-1, so he's going to 6-1. And there it is.
How did you get the 2 from the 1?
Pardon me?
How did you get the 2 from the 1?
This number divides the width. Dividing by 1/2 is the same as multiplying by 2. So when we say we're dividing the width, we mean we're taking every x coordinate and dividing it by a half. Dividing by half is multiplying by 2. So this, if there's a number out in front, that impacts the y coordinate. This one impacts the x coordinate. Right? So just kind of to make sure we're getting this. Let's say we have some function, and it contains the point 6 negative 10. What point would y equals 1/3 f of 2x contain? All right, so think about that for a minute. What does that do? Multiplies the height, which is y, right? Y is the height. So this would be 1/3 times 6, so that would be 2. We're multiplying, oh wait, no. We're multiplying y. So that would be negative 5, sorry, or no, negative 10/3. Sorry about that. This number multiplies the y, so this would be negative 10/3. What does this number do? Divides the x, right? So this would be 3, because I'm dividing by 2. So if the original point was here, in the original picture, when you graph this one, the new point would be here, because it's been divided by 2 on the x, and multiplied by 1/3 on the y. Alright, now we've got the same picture, but we are going to do the absolute value plus 1. So this is another two-step one. But you can do it all together if you want. So pay attention to what's going on. All right, right here. What is taking the absolute value of the whole thing do? That's bottoms up, right? That's everything on the bottom comes up. So, if it's on the top, it stays on the top. Doesn't change a single bit. So that's staying the same. This guy's coming up. And this part is staying exactly the same. So that is a picture of the absolute value. Okay, does that make sense so far? Absolute value of whole problem is bottoms up. Now, what is that going to do? Move it up 1. So we're going to take every one of these points and just move them up 1. And the purple then would be the final answer to the problem. What do you think? Are we okay with that one? All right, the next one. Again, there are 2 things happening. Describe in words what is happening in this problem. What are we going to do? What does this do? That's across the x-axis. What does this do? Well, you got to be careful. It's not an entire flip across y. It's the right side mirrored on the left. So it's not a complete flip-flop. Absolute value of x is right side mirrored onto the left. So this mirrors right onto left. It does not mirror left onto right. You draw the right side as it is, and then redraw it on the left side. So I'm going to start with that. Back to my original. I draw the right side exactly as it is. So here it is. Here's the right side of the picture exactly as it is. Now I'm going to take that and mirror it over here. There it is. That's the absolute value part. That's not the answer to the question, but it's this part right here. That's done. Now, what does that do? Well, you already told me. That flips it across the x-axis. So I'm going to take my picture and turn it upside down. And that one's a little confusing, so I'm going to go ahead and take my black out. And that will be my final answer. Okay, so that's 1.6, folks. Let's do a quick recap of all of the things that we can do and make sure that you have it down. Yeah, that's all I have, 1.6 on my pages, right? Okay, so let's do a quick recap. Make sure we know what we're doing. Let's start with the negatives. What does this negative do? Well, all negatives flip. This one is across, that's right, so reflect x-axis. This one is reflect y-axis. So no one's ever going to ask you to reproduce this, so learn it in your own terms. If you want to say flip it upside down, flip it left and right, that's fine. Use your own words, whatever you can remember. That's the reflections. Now, what about the multipliers? What about, let's make up a number, 5, f of 5x. What about multipliers that you put in there? What does this multiplier do? Multiplies the y, multiplies the height or the y, right? So if that's a 5, it's going to be 5 times as tall. If it's a 1/2, it's going to be half as tall. What does this one do? Divides the x or the width. Divides x or the width. So this picture would actually be shrunk. It would be a 5th as wide. It would be 5 times as tall, but a 5th as wide. Okay, so that's multipliers. Add and subtract, we've already talked about, but let's do it again. A number inside with the x moves you horizontal. It's called a horizontal shift. And we know that if it's a plus number, it actually goes left. And if it's a minus number, it actually goes right. This number is a vertical shift. That means up and down. And if it's a plus number, it goes up. And a minus number, it goes down. That one you already knew, I think. I hope I'm not confusing the issue. You already knew that one. Okay, and then we've got the absolute values. So the absolute value of the whole thing versus the absolute value of just x. So if you take the absolute value of the whole thing, remember, that means positive. You're making it all positive. So that's your bottoms up. Please don't say that's a reflection across the x-axis, because it's not. A reflection across the x-axis would turn the whole thing upside down. All the absolute value does is take the negative part and bring it up. The positive part stays up there. And then, if it's just the absolute value of x, that's when you mirror the right onto the left. So again, it is not a full-fledged reflection. You're not flip-flopping sides. You're drawing the right and then mirroring it onto the left. With this one, whatever is originally in the original picture on the left is just gone. It's gone for this one. And it's replaced with the right side reflection. All right, you okay with that? Okay, we'll have that homework ready to go on Tuesday. And now we're going to start 1-7, which is all about word problems. And some of them we've already talked about. So we're going to need how much time do we have? I don't think we're going to need our book today. We'll need our book next time, but we'll need our calculator this time. So we'll need our calculator. And we're going to do 1.7 number 1, which is, we have a piece of paper. I think I told you before that this is the classic pre-calculus problem. Every calculus teacher in the world expects you to know how to do this. They're going to teach you how to do it by hand without a calculator. We're going to use a calculator to do this. I think we've already talked about this a lot, but let's do it again. So I have a piece of paper. Remember, you made your boxes. And we're going to cut the corners out. And we're going to fold up the flaps. And we're going to make a little box. Remember doing that?
Yeah.
Tell me about the equation for the volume of my box. Remember, the general formula is length times width times height. Tell me what you remember about this for the general formula, or I mean the equation for this particular box. Peeps, we talked about this. The original width was 12, right? What's the new width? Exactly. I don't know who said that, but you're right on target. The new width is 12 minus 2x because we chopped an x off each side. All right. What's the length of the new box? That's the width. What's the length of the new box? 15 minus 2x. And then remember, you're folding up these flaps. So what's the height of the box? X. Just X. X. This comes up, it's X. So there is your equation for the volume of the box. That's what we're ultimately going to type into our calculator. But before we type it in, we have to find the domain. Because the domain is extremely important in any word problem. Because word problems have context, right? So I need to make sure I'm giving answers within that context. So thinking about this piece of paper, thinking about what we're doing, cutting pieces off of it, tell me about x. How big can those x's be? Well, they have to be positive. Would you agree? Doesn't x have to be positive? Welcome to our nightmare.
Oh my gosh, should I just start?
Oh, it happens all the time. Okay, so the domain, whatever x is, it has to be positive. So I'm going to say x has to be bigger than 0. Now, and that should be, I don't know, remember, x is 10. Can I go all the way up to 10? Think about this picture. Can those be 10? No, why not? Because you only have 12. So if you only have 12, and you're taking something off each side, what is the absolute most that you can take off of that side? What? 6? I hope you said 6. I couldn't even hear it. But it's 6. Because if there are pieces being taken off both sides, and you only have 12, then 6 is the most you can take off, right? You can't even really take 6, but you can take everything up to 6. So that's your domain. Now, 6 came from half of 12, right? How come I didn't use half of 15? I got to use the lowest one because while I could take 7.5 off here, I can't take 7.5 off here. So I have to look at the smallest dimension for my limitations. Now, I'm going to graph this on my calculator and find the maximum. We know how to do that. This right here is x min, x max. That's it. That's your domain. If you sketch that, you're going to get a huge curve, and you don't want that whole curve. You want only the piece of it between 0 and 6. Now, everybody should be setting their window, x max. Oh wait, be careful. Are you still in parametric mode? If you're still in parametric mode, you need to go back to mode and choose FUNC, function. That's regular stuff. And then for your window, you have x min and x max. Now, what is y min? Well, what does y represent? The volume. What's the lowest the volume can be? 0. Again, the volume can't be negative. So you got to exclude that. We're not going to look at those points. What's y max? Not a clue. Isn't that the answer to the question? I'm trying to maximize the volume. So you just pick a number. You pick a number. Maybe you let y max be, I don't know, what do you want to pick? 200. When you sketch that, you will be looking for the top of the hill. It isn't a parabola, but there'll be some kind of hill thing there. If you don't see the top of the hill, then what are you going to do? You're going to make that bigger, right? I don't know. I haven't done it, so I don't know what it's supposed to be. Does 200 work for us? Mode. Function. Oh, let's see if we can finish this. Oh yeah, 200 was a good guess. That works great. You should have seen something that looks kind of like this. Looks a little bit different when you graph this equation. Okay, you want x min to be 0, x max to be 6, y min to be 0, y max to be 200. Type in that equation exactly the way I wrote it. Press graph. And it's gonna give you this picture. Now, what do I wanna know about that picture? The maximum. So second Calc Maximum. And just like you did on your last test, we go over there and over here. And this time, because we're doing an actual problem, we have to pay attention to what we come up with. So I got 2.209 and 177.234. That is my maximum point. Now, what was the question? The question was, find the maximum volume. So of these two numbers, which came up on my calculator, which one do I want? My goal is to find the maximum volume.
The Y value?
The Y value. Because when you put this equation in, didn't Y stand for the volume? So if you want the maximum volume, your answer is 177.234 cubic inches. That would be the answer to the question. What does the 2.209 represent? The size of the corners. So if the question had